Okay, hi everyone, my name's Sophie. I'm a senior engineer for Synergy Environ. I'm going to tell you a little bit more about who Synergy Environ are, but this presentation is talking about waste heat and reclaiming it and what waste heat reclaim is and heat networks. So if you know loads about heat networks, you may already know some of this. If you don't, then I hope you find it very interesting. So Synergy Environ, who I work for, is a subsidiary of PD&MS. PD&MS do a lot of infrastructure, oil and gas, and then they own us and Optimus. Optimus did a talk earlier today, and they're doing another one tomorrow. But Synergy Environ, essentially, we provide low carbon engineering and feasibility studies. We do emission reporting, baselining, we do emissions trading scheme support, and as well as preliminary design. But we're doing a lot at the moment on district energy networks, which I'm going to talk more about today. District energy networks, fascinating. I think a real future to the UK and particularly the world. You'll see some case studies from Sweden, particularly. Sweden are leading the market on what they do, and so that's what we're going to go into. So waste, waste, waste. We love waste as human beings. We don't do things very efficiently. In the European Union, excess heat amounts to 2,860 terawatt hours of waste every year, and that is almost the same as their entire energy demand for heating and hot water in building and services industries. So that's a huge amount of waste. If you just use that industry would be sorted. Globally, approximately 72% of the primary energy that we use is lost as heat. And that personally I think is quite spooky because there's the energy crisis and the idea of when it's gone, it's gone. When it goes up into the atmosphere, it contributes to global warming and it's gone. We can't get that back. So I think it's quite spooky if you think about it, that there's just so much lost and it's gone. In London, the Tube, 500 gigawatt hours of heat is lost every year. There are projects to try and reclaim this and use a heat loop technology, but again, it's only starting to happen now. So why is it not happening sooner? In the UK, heat lost through industrial uses is almost 400 gigawatt hours, and that could supply 14% of buildings and services homes with heating and hot water. So again, why are we not using it? So if we now put that into money terms, because that's the most important part of anything, money, how much is that going to save us? And so if we took that 2,860 terawatt hours and we put it into savings, it's £121 billion lost. And that is the same cost as all of the natural gas that was imported into the EU. So you're losing that and then you're buying it again. So it's a double loss. So again, why are we not using more on reclaimed heat? So as I said, why are we not using it? There's a few reasons. High upfront capital costs. So as with anything, it's expensive. District heat networks, still not super well known, so they carry a higher cost. You have to put underground pipes, that's expensive. Drilling, digging, insulating, expensive. Challenges with retrofitting. So the UK is a small country, it's an old country. A lot of our building developments are already here. Look at London, particularly South London, really densely populated areas with lots of houses. It's going to be really hard to dig underneath and put your pipes in. Even when Thames water pipe bursts down the bottom of my road, still takes them a few days to do anything, and that's an emergency. So the idea of a district heat network is going to take even longer. Heat density requirements. So you need a good anchor load, and an anchor load is where your heat is going. Hospitals are great for this. So hospitals are particularly useful in district energy networks, and that's going to be your anchor. Because if you've got spare heat, it does need to go somewhere, hence why it's known as the anchor load. Competition with gas. So this isn't a case of get rid of gas, get rid of oil. As with anything, you need to transition. So Sarah in the Green Scarf did one on earlier about planning with risk, and you've got to plan. And so it's not saying get rid of gas, it's saying let's transition and work together. Getting gas creates waste heat. So why are we not coupling together and using said waste heat? So again, it's limiting the risk and it's limiting the cost. Revenue uncertainty. Waste heat is fluctuating. If you've got a particularly hot day, you might have more waste heat than a colder day, so your prices might change. And consumers are very suspicious of new technologies. We love things that are established. Same with gas. The pipes are all established. Most people are like, I'll just stick to what I know. So again, it's cheaper and it's easier. They'll just go with what they know. They'll keep the lower tariffs. But the danger of that is one day things are going to change and no one's going to be prepared for it. So your 7 pence per kilowatt hour could skyrocket. And we've seen that with electricity. It used to be 12 pence per kilowatt hour, and now you're looking at 28 pence per kilowatt hour. So you need to prepare, again, to take the risk out of what you're paying. Fragmented government. So this isn't quite as an issue anymore because they're bringing in HINTAS, which I am going to go into in a minute, and that's to do with regulating heat networks. But there's not really a one-fits-all policy, and this is the case across the world. Siloed operations, siloed thinking, people don't always talk. And so they are trying to change this, but heat networks, again, they're not really coming together and sharing knowledge yet. But we'll go into HINTAS in a minute. And then what is a heat network? So for me, the big thing is a lot of people don't know what a district energy network is. A heat network, you know, I'll be chatting to friends and I'll be like, yeah, we should use a heat network. And they're just, what's that? Come again? I don't understand what you're talking about. Again, we're so entrusted with what we know. Gas, electricity, you switch the light on, you go to the petrol station, we know it. Change is often a barrier, and the biggest part of that is the knowledge gap. But I'm going to be talking about heat networks as a whole. So what is a heat network? You're taking a central supply of heat and you're taking it to your customers. So often there's different generations, which we are going to go into what those are. But you take a central heat and you pass it in a network. It's pipes that go off to all your customers underground, carrying hot water. They can supply large areas, so you can do towns and cities, or you could do small areas, and they're known as decentralized, centralized models. And the decentralized would be your large area, and then your centralized is, for example, an apartment block. So maybe the shard could run on a centralized system, and each one would take off the network and then pipe back into it when it's got too much heat. Heat networks avoid the need for individual heat sources in every flat. So we've recently done a feasibility study for a council that wants to put all of their council buildings onto a network. And they're going to take all the boilers out of the buildings and just build a giant air source heat pump. And then what will happen is that heat will get pumped into the buildings. So instead of having lots of mini boilers, they're just going to have a giant air source heat pump. And there are lots of technologies that can feed into a heat network. Essentially, if it makes heat, it can go in. So you can use energy from waste, which is where you take, cows and what they produce and you burn it and it creates heat. You can use boilers, electrical, gas, you can use CHP, you can use geothermal, you can use solar thermal. If it creates heat, it can go on a heat network. So here's quite a simple diagram. So this is a fourth generation heat network. And essentially what that means is you've got your heating area, it goes into the network, and then other buildings take off of it. They don't have their own separate boilers, they just take from the network, and it's more efficient. You've then, get a bit more complicated, we've got this one from Scottish Water. So they will reclaim heat from their sewer system, because, let's face it, when we go to the loo, it's normally a little warmer than just cold water. So they can take the heat from that and put it back into the network to heat our domestic hot water. They may need to top it up, which we'll go into in a minute, about high grade versus low grade. And so they'll put a heat exchanger to take that heat out of the sewer system and top it up on a heat pump. So that's the principle of a heat network. This is a fourth generation. Again, I'm going to go into what that means in a moment. Okay, so as promised, the first to fifth generation. So first generation, this was back in the 1900s. They would just burn wood and make steam, and that's how they would power things. Then things got a little bit more savvy about the 1950s, and they started to use oil, and they realised that if they just put the heat directly from the oil into their homes, it would be hotter than using the steam to do something else. They took a step out of the process, essentially. Then you've got the third generation. So this is what most of us know. We have a heat source, and we have it in our homes, and it heats it up. So we have a boiler, switch it on, tiny little bit of piping to the bath, we heat it up. And then in more recent times, we've got a fourth generation, which is these heat networks. So a fourth generation is a heat network. You'll have a central area of heat. It will be connected to all these houses, and they'll all take from the network from this central store. And then you've got, which is not on this diagram, but imagine it's a little bit further along, a fifth generation. So this is brand new thinking, and this is ambient loops. So each generation, you get a little bit cooler on your network. So third generation, you're between maybe 80 to 120 degrees. It's much hotter. Fourth generation, you're between 60 to 80. And then an ambient loop, it's ambient. So it's between 10 and 30. So everything's getting a little bit cooler. And the benefit of doing that is cooler means less heat needs to be generated, less fuel, less money. And things go a little bit further. So an ambient loop, as I said, the fifth generation. This is a nice little diagram, and those who were here yesterday will have already seen this. So you've got all your houses on a network. So let's say the too hot house is in an area with loads of solar gain, loads of solar glare. They really struggle, it's really hot. And then you've got Bill and Geraldine down here, and their house is in loads of shade, and it's just too cold. Instead of the too hot house having to put a fan on or an air conditioner, and the too cold house having to put their boiler on, they use an ambient loop network, which is where everyone contributes and takes off of the network, to pump the extra heat from the too hot to the too cold. On this, you'll see that there are pump stations. That's to move the fluid along, because that is a need for ambient loop, because you need to move it. So electricity is a component of ambient loop technology. And then you've got ground source heat exchangers. So again, I was talking about low grade versus high grade. We're going to go into that. But if you needed this to be space heating, you need to top it up. So hence why your heat pumps come into play. If you just want to use it for washing your hand, these aren't as needed. Okay, so high grade versus low grade. I promised this would be next. So high grade, this can go straight into heating an area. You're needing some warmth, you go for a high grade heat. They're a lot hotter, essentially. Low grade is more ambient, so ambient loops will use low grade. And this is, again, for your washing your hands, for showering, things like that. And again, you can still use this to space heat, but there's just one more step. So you have to put in an extra boiler, an extra heater. So low grade, if you want it for heating, extra step. High grade, ready to go. And you might hear that interchanged and people talking about quality of heat. That's what it means. Okay, so I put this one in because it can be a bit of a tripping point for people. What is a heat exchanger and what is a heat interface unit? And I say that it's like all squares are rectangles, but not all rectangles are squares. So all heat interface units will have a heat exchanger, but not all heat exchangers are heat interface units. A heat exchanger, it takes the water in that's hot, runs through the plates, cools it down, and then that separate fluid gets taken to where it's needed. And you use it everywhere. If you ever find yourself in Dorset, there's a brewery called Palmer's Brewery, and they cool their beer on a giant heat exchanger. It's really old-fashioned, really good brewery tour, highly recommend it. So it's used everywhere. It's such a common piece of technology. Heat exchangers are usually oversized because they're not wildly efficient, so there is a gap in the market for making them better. 3D printing and gyroid structures are threatening to do that, but again, everything takes cost. A heat interface unit, they will have heat exchangers inside them, but they'll also have pumps and meters to take the fluid and to pipe it through to the building. So as I was saying earlier, that council block that had all the boilers removed, and we're going to do a giant air source heat pump, each one of those houses will need a heat interface unit to take that heat and then pipe it around their house. And also, if you're a landlord, you need to know how much heat that they're taking, so hence why you're going to have a heat interface unit. So this slide just shows you what the difference between the two is, because they can often get mixed up in papers, so it's just good to know. And here is as I was describing earlier. So your hot water goes in, and those pipes are separated from the other fluid, they interact with each other, and the heat is swapped over. And so the fluid that's in your system in your house will have picked up the temperature, and then the other fluid goes back outside to either be reheated or to do what else it needs to do. All right, so I talked about HINTAS a little bit earlier. HINTAS is a new regulation that's just been released, so it's still available to comment on. So if you have opinions on heat networks, or you believe that there's a gap and it needs to be addressed, you can go and comment on it. And it's being run by Fair Heat and Besser, and so you can go online, have a Google, and read what they've done, and just see what your opinion is. And so it's not coming out for a while. They think it's going to be about 2026, but as with anything, who knows? Who knows? So have a little Google on HINTAS so you can have a comment on it and see what you think. But the regulation is ideal to make everyone work from the same hymn sheet. It's to improve performance and the outcome for the end user. And it's to make the networks more reliable. I think they're trying to avoid what's happening with the electricity grid, in that there's too much demand on it now, and we're struggling to adapt. We're struggling to put extra substations in, all that jazz. So I think they're trying to do this earlier rather than later to make sure it's reliable and we can kind of plug and play with other heat networks. If you have a heat network, it basically applies to them all. Whether it's old, new, it applies to you. I didn't intend that to rhyme, but there you go. That's applies to you, any heat network. So it happens before the design, it happens before the construction, and it happens before the operation. It also happens 2 years after operation. They want to make sure that what you're doing is A, what you promised, and B, that it continues on. Because there's a lot of things you can design to a certain specification, and then if it's not followed up on, you can kind of do whatever you want. So they're trying to get rid of that in heat networks. So how can you prepare? So there's lots of ways to keep on track about HINTAS and what it is. You can email the Heat Networks regulation at Ofgem, and you can ask to receive regular updates, and they will send you emails, newsletters about what's going on with HINTAS. You can utilise the heat training grant. So and unfortunately it's only England residents, but every England resident can get £500 towards training. So you can go online and do a course, and there's no cost to do that. You want to keep abreast of news. So BESA, who are running the training, they are the lead of all this. And so if you go on their website and sign up to notifications, they'll keep you posted on what's happening in the heat network world. And then for any other questions, heat networks, energy security, those are, making sure that everything's legal, complying, and everyone's up to speed. Now, the government is very aware that this is a big change, so they are trying to help businesses not have too large of a risk to their business. So they are trying to make that, in their minds. So again, that's why you can currently comment on it. It's open for comment, and they just want to make sure that it's easy, because not many things to do with regulations are. When you do this, you'll have to submit on a portal once you've done your heat network regulations. So anyone that's been involved with ESOS, that's a really good example of a government portal, is every so often you have to go on and submit data. So it's just going to be a government portal where you go on, submit data, and just say, look, we are performing as we promised. Okay, so Sweden's work, I did talk about Sweden earlier. They have a district heat network infrastructure. They're doing a really good job. And so if you want to see the best of the best, go for Sweden. Now, a danger, I think, for UK businesses is a lot of European countries, so Denmark, Sweden, Finland, they're doing this really, really well. So their businesses are now coming over here because we've started to open up a district heat network. If we don't do something about it, we're going to lose business to them, which is fine. They're very good at what they're doing, but we need to make sure that we're ahead of the game and start talking about this amongst ourselves. Otherwise, UK businesses won't get an opportunity to have a go. So Sweden's district heating infrastructure, 57% of all the buildings were supplied by heat and hot water off of this network. So they're all connected to each other. And then 45% comes from waste heat. And what I think is more impressive is when you look at what happens to their waste. So in London alone, and this was from the London plan in about 2018, so it's a bit old, but I do recommend a Google. The waste of the food that London throws away is over £1 billion worth of waste. So that's just going in the bin. It creates methane, and methane is 15 times worse than carbon. So, but people aren't talking about that in the same way. Sweden, they take all of that and then they sort it. They take their recyclable stuff off to one way, they take their food to another, and then they use energy from waste. They create methane, they create heat. So only 1% of their waste now goes to landfill. Ours is not that. I can tell you that for a fact. At the bottom here, we've got thermal tanks. Thermal tanks is something I think that's really interesting, and it helps what's known as smooth out the peak, and I'm going to talk a little bit about that on the next slide. Thermal tanks are installed to make sure that when the heat is generated, if it's not needed straight away, it will be used later. So nothing goes to waste. And that's from this very crude and simple graph, but essentially heat required, a low amount, the incidences are really high. Heat required, a high amount, the incidences are a bit lower. And what that means is often people would design for the maximum peak on a network. They'll do equals max on Excel, find that, and then they'll look for a heat pump that's that size. But if you want to make it more cost effective, you want to smooth out the peak, you want to get rid of it. So you're going to size for lower. I'm going to install a lower heat pump, and I'm going to install thermal buffers. And thermal buffers are a lot cheaper. You can fill them up and use them later. So instead of having to buy the world's biggest air source heat pump or the world's biggest boiler, you think, I'm going to do half of that, because realistically, the amount of times that Mike is having a shower at 2 a.m. at 100 degrees is quite limited. So I'll just fill up this buffer just in case. And I think this is really interesting, and it's starting to become more and more talked about. And if your engineer isn't talking about it, then they should, and get yourself a new engineer, because it's common practice and it should happen. Okay, so Swaffham Prior Heat Network. I can't talk about any of Synergy's work because we haven't been given permission. So this is one that you can find online, and it's by a company called Bouygues Energy and Services, and they worked with Cambridge County Council. So like I said, there's loads of information online, and this is a really successful example of a heat network in the UK. So Swaffham Prior is a village out in Cambridge, and they decided that they'd had enough with their houses having to get oil delivered. There was issues with that. You have to buy the oil, so the resident can't buy it in a bulk. Then they can't get their oil, so it's kind of threatening fuel security. There's a lot of emissions having to drive the oil backwards and forwards, and oil itself is not that popular a fuel anymore, so it's quite difficult to get hold of for some people. So they did this. They built a massive solar array, because they said, right, we're going to use the sun to power this, instead of having to take it off the grid. We're going to use ground source heat, and we're going to build these massive boreholes, and the deeper you go with the borehole, the more temperature you're going to get. So they built, I think, they're 19 kilometres deep each. That then goes into a thermal store, ready for when Mike has his 1 a.m. shower. And that's got backup boilers in there as well, just in case that it's not hot enough in the ground or the air source hasn't been able to top it up. And that's there just as a backup. They've then also got air source heat pumps, which top up the thermal stores, and they're powered by the solar array. So again, they're not having to use too much from the grid. So they're not having to take off the grid, which is a problem, because anyone that deals with UKPN knows that mobilisation works and the cost involved is quite difficult. So if you can bypass that, that's good. Then that all goes to the homes. They get 72 degrees because it's topped up from this air source heat pump, and they don't have to pay through the nose for it for oil and gas. For oil, I should say, and it's safe and it's done. And that's done now, operating. It's really successful, and it's been a bit of a hit. So again, and this is a rural village, and I know it said it's better for clusters of homes, but because they're all contributing, it works really well. So yeah, have a Google of this, it is good. So your roadmap to waste heat. So this is the last slide, and this essentially talks about the different steps that you need to do to get your waste heat and how you're going to utilise it. So the first off, identify the heat source. What is your waste heat? So maybe you've got an oil rig somewhere and you're drilling and you're creating loads of heat. Let's take that. Maybe you're doing cutting and the heat generated from the blades. Let's take that. There's a lot of waste heat out there. Maybe you've got loads of waste. I don't know, we had an MDF company. They had loads of chippings. They wanted to use that instead of just getting rid of it. They were using energy from waste to help power the warehouse. So again, what have you got that you can use to create heat? We're then going to go assess the local demand. Is your demand enough to use all this waste heat? Or do you need another anchor load? Do you need yourself a hospital? Do you need yourself a housing block? So where can we put this heat? Because as again, we've always got to plan. If we don't plan, we fail. Feasibility and appraisal. So this is my favourite bit. No idea is a bad idea. What can we do? How can we make it better? Can we put a solar array in? Should we do ground source? Should we do air source? Should we even go and do crazy? Let's go for water source. So no idea is a bad idea. You can kind of make a long list and you can make your short list. Then we go on to stakeholder engagement. Now this is my least favourite because even if it's a good idea, they still hate you. Don't matter what happens when you deal with the public, they hate any change. So this bit is often good if you can get a company to do it for you. And I'll plug an RSK company. There's Copper Consulting. They do all of that. So where I can, I'm like, you deal with that, thank you. But again, it's to make sure that the public are happy with what's going on because the success often is communication. Business modelling and financing, so there's a lot of grants available now. The Green Heat Network Fund is still around, so I do recommend keeping abreast of that. You can sign up for newsletters on there, so that's really useful, and that's a lot of money that's available. After all that's done, so the techno-economic assessment model, or it gets shortened to TEAM, is done, you can then move on to design and engineering. So this is when you're going to get your engineers in, you're going to design it, you're going to make sure it works. At Synergy, what we then do is we work with the designers to try and break it. So we'll use a software called Energy Pro. There are other softwares available, but that's the one we like. And Energy Pro will put the design in, we'll model the heat network, and we'll see if it works and if we can break it. And that's just to make sure that you're taking out a step at the end that it might not go wrong. But we're like, well, let's say Mike's had 2 weeks of 1 a.m. showers that's super, super hot. Is that going to break the network? No. Okay, let's go to build. We then go down to planning and regulatory compliance. So again, you need to make sure what you're doing is going to be okay. Have the government given you approval? Have you got any Barbastelle bats? Have you got any great crested newts on site? Let's go find that and just check. Procurement and construction, kind of says what it says on the tin. You're going to buy it and you're going to build it. Commission and operation, you're going to make sure it works and hand it over to the client. You're going to give them your O&M manuals because they need to know what's going wrong and how it's working. And then finally, measurement and verification. So if you've got your loan through an energy performance contract, so EPC, and EPC is used as an acronym for so many things, but an energy performance contract is this one, you'll need to have a measurement and verification part to it. And that's when you're going to get a measurement and verification analyst who's qualified to check. And essentially what they do is make sure that what you promised to build is performing and that you can pay the money back to the bank that you got the loan from. Measurement and verification contracts are a really good way to how people who don't necessarily have the upfront capital build these projects and deliver. All right, thank you for your time. Any questions? Okay, so good question. So is it for private or government? It's for both. So it's more difficult with private because it is harder to sell it to the end client. There's a company that's come over from Denmark who are doing it in a UK real estate. They've got Greggs and McDonald's, and both of them produce a lot of heat. So they're putting it back onto the network, and the way it works is how much heat goes back through the meter. So it's what you're taking off of the network as opposed to what you're giving, and then they can charge a unit price to that. It is more difficult for private investors because the Joe Public have issues with fluctuating tariffs. We're very much used to peak and off peak, but you will have fluctuating tariffs. So again, you can do that, but it takes a lot more market engagement, much more community work, things like that. But the government also is doing it. You'll see it a lot with local councils, and it's good for sort of council estates where they've got a lot of buildings. So it is for both, but the sort of capex model is very different because for government, they're doing it to reduce fuel poverty, so they don't mind how much they spend. Whereas with private investors, you need to make sure. So I think the difference is how much you're consulting with the public. So for private, you've just got to do a lot more, unfortunately. Okay. Any more questions? No? Okay, good.